In this video we're going to continue looking at material in chapter 4 on grouping objects, and we're going to introduce the while loop. The while loop really is the most important loop that you're likely to use in Java, and we're going to look at it in particular because it illustrates the difference between bounded iteration, as we've seen with the for each loop, and unbounded iteration. In other words, that we often can't anticipate at the start of the loop how many times the loop will actually be executed. And we're going to make a contrast between the for each loop's behavior and the while loop's behavior. We're also going to illustrate that the while loop is commonly used for non-collection based tasks. This is because it is a much more flexible loop than the for each loop. We've seen that a for each loop repeats the loop body once for every object that's in the collection that's being iterated over. And sometimes we require more flexibility than this, and it's exactly that the while loop supports. When we use a while loop, then we need to express a boolean condition that states whether we wish the loop to continue iterating. And this is an extremely flexible approach, because the boolean condition can be either simple or complex, involving lots of different subconditions. And we'll see the while loop used in a context other than with collections as well. This is the syntax for the general form of a while loop, and we could characterize it as expressing the idea that while we wish to continue, in other words, while the loop condition evaluates to true, we want to do the things that are inside the body of the loop. So a while loop is introduced by the while keyword. There's then a boolean test, which if it evaluates to true means we'll execute the body of the loop at least one more time. The body of the loop codes the actions that we wish to perform on each iteration. And then once the loop body has been completed, we go back to re-evaluate the loop's condition to see whether it's still true, and if it is still true, then the loop body will be repeated again. And that process continues until the loop's condition evaluates to false, and then we move on to whatever follows the while loop. Here's typical pseudocode for the way that we'll want to set up a while loop if we're going to iterate over a collection. So we're initially going to look at a while loop in a context similar to those we've seen before, using a for each loop, just to see some of the differences between using a while loop and a for each loop. So part of the flexibility of the while loop adds complications when we wish to use one. There's more setup that we have to do, and there are more actions that we have to take inside the body of the loop in order to ensure that the loop eventually terminates at an appropriate point. So when used with a collection, we're typically going to be stepping through the collection from element 0, element 1, element 2, and so on. So we need to declare an integer variable that's going to store the current index value for the next element that we want to examine and potentially process inside the body of the loop. So we typically declare an integer variable just before the start of the loop. We initialize that loop's value to be 0, ready to be the first index into the collection. And then we immediately test the condition. Now it might seem strange to test the condition before we've actually done anything with the collection, but by testing the condition before we do anything, we cover ourselves for the collection potentially being empty. Because if the collection is empty, then there's nothing to process, and therefore we don't want to execute the body of the loop. So that condition coming first is a really important feature of the while loop. It actually means that the body of the while loop can be executed 0 or more times, and not simply 1 or more times. Assuming that we do wish to continue, we then enter the body of the loop, and the first thing we're likely to do is to retrieve from the collection we're iterating over the next element. So we're probably going to make a get call on the collection, passing in the current value of the index variable that we set up before the loop. Having retrieved that item, we're then probably going to want to do something with the element we've just fetched. And then a really important final step at the end is to make sure that we increment the value of the index variable so that the next time around the loop we will be processing the following item after the one that we've just processed. So we declare an index starting at element 0. Inside the body of the loop we fetch the next element, typically into a local variable. We then process the element in some way, and finally we make sure that we increment the index variable ready for the next element. Now, because we're drawing a contrast between the way that a while loop works and the way that a for each loop works, it might be helpful just to review the for each version of the list all files method from the Music Organizer project. We read the body of the method as meaning for each file name in the files collection, we want to print that file name out. So every single file name in the files collection is retrieved and processed. Here, for comparison purposes, is the while loop version of the list all files method. And hopefully you can see that all of those typical elements that were introduced on the previous slide with a while loop on are present. We've declared a variable, which in this case we've called index, immediately before the loop, and we've initialized its value to 0. Then the loop's condition says as long as the value of index is within the valid range of the indices for the items in the files collection. So as long as index has a value that's less than the size of the collection, in other words the number of items in the collection, then we know there will be at least one more element in the collection that we can retrieve and process. So we enter the body of the loop, we make a get call using the current index on the collection, store the result in a local variable, process the file name, which simply involves printing it out, and then finally inside the body of the loop, that very important step where we increment the value of the index so that the next time around when we come to check the condition, we're gradually increasing index so that it will ultimately become equal to files.size, and therefore the loop will terminate. So if we think about the differences between those two versions, the for each version of list all files and the while loop version, we see that with the while loop version we have to explicitly declare a variable to hold each element's index, and we don't have to do that in the for each version. The for each header takes care of setting the loop variable to each successive item that's in the collection. So we've got an extra variable declaration in the while loop version. We must express the Boolean condition correctly to ensure that the loop will only continue as long as it's reasonable to continue and will stop once it's not reasonable. So it would not be reasonable to continue if the value of the index is too large for the number of items that are in the collection. Then once inside the body of the loop, we have to explicitly retrieve the next item that we're interested in. That's the equivalent of what's done in the for each loop's header, but here we have to make a get call on the collection, pass the appropriate index in, and then once we've done the processing, we must explicitly increment by 1 the index into the collection. And again, that's something we don't have to do in the for each loop. The for each loop manages the sequencing of retrieval of the items from the collection for us. So if we're to summarize for each versus while, then we can probably recognize that the for each loop is much easier to write. There are fewer things to think about and potentially get wrong. The for each loop is also safer in the sense that it's guaranteed to stop. It manages the sequential processing of the items in the collection for us. We don't have to worry about incrementing indices. We don't have to worry about checking the right condition in the Boolean expression in the loop. So it's much easier to write. Now when writing a while loop, we actually have to be very careful, because if we get either the condition wrong or the incrementation of an associated collection variable wrong, we could end up with what we call an infinite loop. That is a loop that, once entered, never terminates. Every time we come around and test that loop's condition, that loop's condition is going to give the value true and never become false. And we'll see an example of that shortly. However, the while loop offers us some important flexibility. We've seen that with a for each loop, once we're committed to iterating over the collection, we're going to be visiting and potentially processing every single item in the collection. And if that collection is very large, that could take a large amount of time. However, because of the flexibility of the while loop's Boolean condition, we can arrange for something to be set inside the body of a while loop that means that once we come back around to evaluate the condition, the continuation condition is going to evaluate to false, and therefore we can stop partway through processing a collection. We're not committed to processing the whole collection when we're working in the most general case with a while loop, and that's a very, very important feature of while loops. It's also what gives them this indefinite iteration characteristic. We know with a for each loop, once the loop starts, we know how many items there are in the collection, therefore how many times the body of the loop will be iterated over. Typically with a while loop, when we start the loop, we don't necessarily know how many iterations it's going to take before that condition becomes false. And that's why we have this characteristic of indefinite iteration. So that we don't get too hung up on the idea of using loops with collections, and to show the flexibility of while loops for other situations, it's probably worth looking at a couple of examples where the while loop is used in a situation that does not involve a collection. Here's an example, fairly trivial, but it does illustrate the point, where we wish to print out successive even numbers in the range 2 up to and including 30. So we have a variable initialized to 2. The condition says that as long as that variable's value is less than or equal to 30, we want to go inside the body of the loop. Inside the body, we print out the current value of number, and then we add 2 to number, because we're interested in even numbers, go back around, evaluate the condition, so we can see that that loop is going to output the values 2, 4, 6, 8, and so on, all the way up to and including 30. But there's no collection involved. We're not retrieving any items from a collection. We're not processing a collection of numbers. We're simply manipulating an integer variable, changing it each time, and then printing out its new value until the value becomes larger than we're interested in. Here's another example. We might imagine that there's a program we're running, and the program requires us to answer either yes or no, or at least type y or n to indicate a yes or no answer to some question that it's posing. And the program insists that we type either y or n and is not satisfied with any other answer. So the while loop is going to continue as long as our answer is neither a y nor an n. So it's worth taking a little bit of time to examine that Boolean condition and understand what it's testing. It's saying while the answer is neither y nor n, we want to go inside the body of the loop, print out the prompt, and then read an answer from the user, come back around and make a test of the answer that's been received. Now notice that what we've done before entering the loop is we've initialized the value of the answer variable to be something other than y or n. So we know that the body of this loop is guaranteed to be executed at least once. We'll get a prompt and then a request for an answer. So that's worth taking note of as a way to ensure that the body of a loop is executed at least once, by ensuring that the condition will evaluate to true the very first time the loop is encountered. Now, clearly, there will be an indefinite number of iterations every time this loop is executed. We can't know in advance how many responses the user will make before they respond with either a y or an n. And it could be that on 99% of the executions of this loop, the user immediately answers with either a y or an n. But they could mistype, misunderstand what it is that's being asked, and how many times they do that is unknown. so the number of executions is indefinite, and the while loop fully supports continued prompting until the user provides exactly either a y or an n. So that's another nice illustration of the use of a while loop for indefinite iteration aside from processing a collection. Here's a slight variation on the example that you've just seen, and this is an example of an infinite loop. And it's worth just taking a moment to consider this and appreciate firstly that it does indeed lead to an infinite loop. This loop will go on and on and on, printing the prompt y or n, but it will never terminate. It will go on forever. So the reason is very simple, but it's also a very important feature of why we often end up with infinite loops. Clearly, what's missing from the body of the loop is any reading from the user of their input. There's simply the prompt and no reading. So what that means is that the value of answer never changes. It's set to a question mark before the loop starts, and nothing inside the body of the loop can result in that variable having a different value. So that's a very interesting feature, but it's quite diagnostic of why we get infinite loops. In most cases, the reason why we get an infinite loop is that there's nothing happening inside the body of the loop that could cause the loop's condition to become false. Remember that once we're inside the body of a loop, the only way we're going to leave the loop is when we come around and evaluate the condition and it's become false. So if there are no statements inside the body of the loop that could ever cause the condition to become false, or those statements could never be executed, then we're in the situation of having an infinite loop. So it's worth studying this example and just bearing those circumstances in mind that will often lead to an infinite loop. A fundamental activity of programs is the need to search. So we often have collections and we want to search through a collection to find, for instance, all the items in the collection that match some particular condition. Or we might want to search a collection to see whether something we're interested in actually exists within the collection. And a while loop is the ideal type of loop to use for searching. In fact, it's really the only kind of loop that we should use for searching. We should never use a for each loop to carry out a search task. It's simply not an appropriate thing to do. Now, searching is necessarily an indefinite process. If we're searching for something, we can't know in advance how many items we might have to look at before we identify what it is that we're looking for. Indeed, we might never find the thing that we're looking for. The search might fail. So it's very important that when we're writing the condition of a while loop, we take both of those circumstances into account. We need to code the condition in such a way that it will become false if either we find the thing we're looking for or there are no more places to look for the thing. And that can be quite tricky, but it's an essential element of writing the condition of a while loop, and we'll see in practice what that means for us in a moment. So to reinforce this idea that search tasks are necessarily indefinite and therefore well suited to use with a while loop rather than a for each loop, consider the idea that you might be about to leave the house and you need to search for your keys, your house keys or your car keys, whatever it might be. The fact that you need to search means you don't actually know at this point where they are, and therefore you cannot predict in advance how many places you will have to look before you find them. You simply know that when you find them, you'll stop looking. If you knew where they were, you'd immediately go and get them, and it wouldn't really be a search process in the first place. Here's how we might express the search process for your keys in the form of a while loop. In fact, we've expressed it in two separate ways, but ways that are equivalent and ways that you might commonly see searches expressed when you're looking at program code. In the first case, what we're saying is, while the keys are missing, we clearly need to look somewhere else, so we need to execute the body of the loop And so while the keys are missing, we look in the next place. Now the hope is that the process of looking in the next place will result in us finding the keys, and therefore the keys will no longer be missing, and the next time we come around to evaluate the condition, that condition will now be false. So that's the basic structure, the basic form for how we might code up a search when expressing it in the form while something is missing or while we are still searching effectively. So the top version is saying while we're still searching because the keys are missing, look in the next place, hopefully we find them and we will no longer be searching and the loop will terminate. The difference is subtle, but it's worth observing. In the second version, we are expressing it in a slightly different way. So our goal is to find the keys. And if the keys are missing, then we clearly haven't achieved that goal yet. So we can express it in a slightly different form by saying, while not, the keys have been found. So if the keys have been found, then the result of that will be true. The not will turn the true into false, and the false will cause the loop to stop. But in the initial stage, the keys have been found is false, so not false becomes true, and because the loop's condition is true, we'll go into the body of the loop and look in the next place. And again, the hope is that by looking in the next case, the keys will have been found, and if the keys are found, then when we come around to the condition, not true gives false, and the loop will terminate at that point. So subtle differences between the two ways of expressing this, but we'll see source code examples of how that might work in practice in a searching the collection scenario. So here's the first version expressed again in the form of keys. We're likely to define a Boolean variable called searching, which we set initially to be true because we are still searching at the point where we begin looking. So the loop's condition necessarily evaluates to true the first time around. We enter the body of the loop. We check to see whether they are in the next place that we look, and if they are, we're no longer searching. So we change the searching variable to be false. And so now when we come back around the loop's condition will evaluate to false. But if we didn't find them in the next place, then searching will still be true. We'll go into the body of the loop again, look in the next place. Again, if we find them, searching is set to be false, and so on and so on. Now, there's clearly a potential for an infinite loop here. We're only setting searching to be false if we succeed in finding the keys. If we don't find them, then there is no escape from that loop. Now, in practical terms, if we really were looking for our keys, there will be a limit to the number of places we could look. We'll pass over that for the time being, but it's worth just appreciating that there is potential for an infinite loop if we never find the keys and just go on and on and on searching. Let's look at the alternative way of expressing this. So in this case, instead of having a Boolean variable searching set to be true, we've got a Boolean variable called found, which we set to be false. And now, because the value of that variable is the opposite from the previous version, there are two other places within the loop's condition and the body of the loop where again there's an inversion of the Boolean elements of the search process. So now we want to say while not found. So found starts at false, not found will be true initially, we'll enter the body of the loop. And then if we find them in the next place, found will be set to true, we'll come back around to the condition, not true will be false, and at that point the loop will finish. So it's important for you to pay careful attention to the differences between those two ways of expressing the same search. So it's the same search, but the way we express it in terms of how the condition is defined are critical. And depending upon the circumstances that we're coding, we might choose to use either one form or the other form, we wouldn't mix the two forms in any one situation. We use one or the other. So let's move on from the hypothetical situation of looking for keys, and now let's think about searching a collection for a particular item that matches some condition. So we're back again with our music organizer project, and what we're interested in finding out is whether there is a file name inside the collection that exactly matches some particular search string that we're looking for. So there's a difference between this version and a previous version where we were printing out selective file names. In the previous case, we used the contains method of the string class in order to find whether there's a substring in the name of a file that matched some term like early or blues or something like that. Now we want a complete exact match for the search string that's being passed in as a parameter to this isInCollection method. Now, there's quite a lot of code here, but if you look carefully, what you'll see is that the core elements that we illustrated earlier on, setting up an index variable, checking whether the variable was still in the range of the collection's valid indices, and incrementing that index variable, those are all in place. So you can identify all of those. And I've highlighted in a different color really the core elements associated with the searching process. And again, these are very similar to the example we just looked at, where we've got a searching variable that's initially set to be true. So one of the core differences between this while loop and the previous ones we've seen is that the loop's condition has two parts to it. Because remember, we need to code the condition both for the cases where we might fail to find the thing we're looking for, and for the case where we might succeed in finding what we're looking for. So the two parts of the condition cover those two success and failure exits from the method. So what the while loop's condition says is, as long as there's at least one more item to be considered in the collection and we're still searching, in other words, we haven't found it on a previous iteration, then we want to go inside the body of the loop. Then we fetch the next item from the collection, the next file name. We then process that file name, where the processing involves making a string comparison. Is the file name we've just retrieved exactly equal to the search string we're looking for? And if it is, then we can set the searching variable to be false, and that's going to cause the loop's condition to evaluate to false. However, if we don't have a match here, we need to make sure that the index variable is incremented by 1, so that on the next pass through the loop's body, we'll make the test on the next item in the collection. So this is merging two different things that you've seen with while loops. We saw the basic structure of how we use a while loop to iterate through a whole collection, but we've added in the elements that then allow us to finish the iteration early if we succeed in finding what it is we want. And we saw those elements in connection with searching for keys. So this is like a pattern for how we might search a collection for something. So it's really worth spending some time making sure that you understand how this works. Let's just spend a little bit more time thinking about that loop's condition, because it's important. We need to be confident that we understand the two aspects that either cause the loop to continue or cause it to terminate. So we need to continue as long as the index is still valid, as long as the index is less than the size of the collection. But we also need to be true the fact that we're still searching. In other words, the searching variable wasn't set to false on the previous iteration of the loop's body. So what that means is we'll finish a search when either the index variable has become greater than or equal to files.size, or when the item's been found. In other words, when searching has been set to be false. Now, it's probably worth looking at the alternative way that we could have expressed this, So instead of having a searching variable set to be true initially, we could have a found variable set to be false. And there are just a few places where there are differences. Remember that the found variable is set to false, and therefore in the condition we're now interested in continuing as long as we haven't found the item. In other words, not found needs to be true. And then when we find the item, we set found to be true so that that not found becomes false and will trigger the loop terminating. So these two versions of searching, with either the searching variable or the found variable, are identical. It's only the way that we express the search that causes the differences. Otherwise they operate entirely identically. We'll find the item in the same number of iterations, we'll always find the same item, and so on. There are no other differences other than the way we've chosen to express the search. So a question worth thinking about is, does the search still work if the collection is empty? And the answer is yes, it does, because the test of the index against the size of the collection will give false on the first evaluation. So if we set index to be 0 and the size of the list is 0, then 0 is not less than 0. And so that test of the index will give a false value in the condition, and so we won't enter the body of the loop. So it's important to stress that a significant feature of a while loop is that the body of the loop might actually be executed 0 times on any particular execution of code involving it. So if we summarize on the searching aspects that we've looked at, searching is a fundamental activity. It's something you'll come back to again and again and again, and so it's worth almost committing to memory the kind of pattern that we've seen for the way to express search through a collection. Search is also applicable beyond collections as well. We may be searching in other circumstances. Search is necessarily indefinite. We can't know in advance how many iterations we'll need to perform before we find the thing we're looking for. And indeed, we also have to recognize that we might not find the thing we're looking for. So we have to code for both success and failure in the loop's condition. So we spent quite a while thinking about a while loop. And one of the reasons we've spent such a long time thinking about it is it really is the most important type of loop to be able to use. While Java has several different types of loops, if there's only one that you get to fully understand and be confident using, then make sure it's a while loop. Don't become fixated on the for each loop simply because it's the easiest to use. There are many circumstances where it's not appropriate to use a for each loop because you want unbounded iteration, indefinite iteration. And we've seen in the while loop version of the list all files method that we can still get bounded iteration with a while loop. We're not prevented from getting that. We can code it according to the circumstances that we're working with. We've also seen that a while loop can be used both with collections and independently of collections, and we saw that with the printing out of the even numbers and the prompting of a user for a response. We always have to bear in mind when using something like a while loop that we could end up with an infinite loop, in other words, a loop that doesn't terminate. And sometimes that will be manifested by the program endlessly doing the same thing and maybe printing out the same thing. Sometimes there may be no external manifestation. It may be simply that the program is no longer responding to a user and it seems to have gone away and died. And that can be an indication that it's gone into an infinite loop from which it cannot escape.